So, rational exponents. Exponents that are now fractional. And the thing we need to remember with rational exponents is the denominator is the root number, the numerator is the power number. So, given any fractional exponent, that's the key here. So here we have a couple examples of why is it that something to the fractional exponent is equal to a root. Let's check this out. 1/2 to the second power becomes just b. Square root of b squared also becomes b, so that means if they're both b, that means square root of b must be equal to b to the 1/2 power. Huh. And then this third one, this right here, that's probably the big one to remember. Sometimes I want to take a root first, and then raise to the power. And other times I want to do power first, and then raise, or not raise, but take a root. Some of these problems would be problems that would be on a no calculator portion. Chapter 6, we did this algebra 2, chapter 6. We handled this. So our properties from yesterday, same basis, add the powers, multiplying, subtracting when you're dividing. Power, powers, all of those still apply, even though we've got fractional exponents. It's the same thing. So let's actually see how we can use this to simplify. So all of these that we're going to do right now would be a non-calculator type of problem. You don't need a calculator for this. Not that bad. So again, keep this in mind. This is what you got to remember. For any exponential, doing it again, that's your power number. That's your root number. Okay. So 16 to the 3/2 power. Would you rather, A, take 16 to the third and then find the square root of it? Or would you rather take the square root of 16 and then raise that to the third? Yeah. I would too, yeah. It makes a little more sense for me to do the root first. So in this one, we're going to take care of the root first, and then we'll take that answer and raise it to the power. So that means we get 4 cubed, or just 64. Versus saying 16 to the third, well, I'm trying to do that in my head, that's a little bit of work, right? And then take the square root of that big number, man, that's a lot of breaking things down. And I don't want to have to do that if I can just take care of the radical particle first. Okay, now notice these next three. All we're doing is we're introducing this negative, but we're introducing it in a way that they're all different. First time in part C, negative is just hanging out in front of the 6. And then in part D, it's part of the 6. And that changes our answer. So maybe we should look first at 6 to the 3/2. Now, is that a problem that I would do root first, or is that a problem I would do power? Now, here's how you tell. If the base number happens to be a perfect root of whatever that denominator value of your exponent is, then you can do the power, or the root part first. So, for example, if that was a 9 to the 3/2, I would take the square root of 9 and then raise it to the third. But 6 is not a perfect square. So I don't have to worry about doing the root first. We're going to do the power first. So we're going to do 6 to the third, and that whole thing we will square root. And that's the square root of 216. And then now we have some work to do. So oftentimes when you go this route, you're going to have some work to do. I'll show you another way to think about this. Square root of 216, 36 times 6. So this becomes the square root of 36 times 6. And the square root of 36 is 6 with the square root of 6 left over. So that would be my answer to that one. How about thinking of it using exponents? Another way to write 6 to the 3/2 power is to write it using a product of two base power numbers. Meaning, 6 to something power times 6 to something power must equal the same thing as 3 halves. So what am I going to add together to get 3 halves? Which 2 halves? 1 half and 2 halves. If I add 2 halves and 1 half together, I get 3 halves. Well, this makes it a little easier. We don't have to worry about having to simplify the radical, because what's 6 to the 2 over 2? That's just 6. And what's 6 to the 1 half? It's the square root of 6. And so this is the same thing as 6 root 6. So it's another way you can think about doing these problems. Simplify the radical power, not the radical power, simplify the power number to go from there. All right, now with the 6 root 6 as the basis for our next two, for part C, my answer would just simply be what? Negative 6 root 6. This negative in part C is not being affected by the 3 halves power. But in D, it is getting affected. So this is just negative 6 root 6 because the negative is out in front. However, now the negative is a part of the 6, which means it does get affected. And this now becomes the same thing as saying, again, using powers first. Negative 6 to the third, which is negative 216. So we're going to get an imaginary guy here. Pull out that I. We get 6i. Root 6 to that. So, how do you get C? Well, C is just the opposite of D. So the negative is not without the first. Negative 6 3 halves. Same thing as saying negative 6 cubed square rooted. Negative square root of 216. Negative 6. Unless there's a parenthesis around that negative, you can't assume it's being raised or not.
Are we going to get negative exponents?
Yeah, we could have negative exponents. Yeah. So what would it do in these problems? What would I do differently if they were negative? Huh? I'm just going to flip them. Yeah. Yeah. So like if that was 16 to the negative 3 halves, it would become 1 over 16 to the positive 3 halves, which is now my answer of 1 over 64. The process doesn't change. It just move them to a different location and do the same thing. All right, let's move on here. Cost of shoes t years from now is given by the function c of t equals 62 times 1.05 to the t power. So yesterday we learned that c of t equation is pretty much the same thing as the one we were working with yesterday, this guy. A of t equaling a of o to the 1 plus r to the t power. That's our generic exponential function. So checking out these, find the cost now. What immediately maybe you would look at that and you think, wait a second, am I missing something to be able to answer that question? What do you think? Yeah, you think, okay, what is now? Does it really matter? If now is just t years from today, tomorrow, a week from tomorrow, whatever, does that change how you would solve and answer part A? No, it doesn't. Because what's the answer for part A? How did you get 62? What's on the equation? Okay, and what do you mean it's in the equation?
Like the A of O is where it starts.
Exactly. The A sub O is your initial amount. That's how much the shoes are going to cost prior to me raising them or lowering them at some given rate. So that's one way to come up with 62. What's the other way I could have come up with 62? Huh? I don't want to solve for t because I'd be looking for time. But I make t equal to what? Not 1.
0.
0. And t equals 0, we haven't done it. So t equals 0, it'd be 1.05 to 0, which is 1. And 1 times 62 is just 62. So the answer for part A would just be either A of O, which is $62, or you do A of 0, and that's the same thing. 62. What about B? Time that costed 2 years, 6 months. Now, here's where you got to pay attention to what does T represent. Because maybe T would represent months. But is that what the problem stated, the original problem? So pay attention to the time period that was given to you. This was T in years. So my answer I have to use there must be a year number. How do I make that a year number? Yeah, you think that's not rocket science. So 6 months is half of a year. So 2 years, 6 months is equal to 2.5 years. So I'm just going to use now decimal values. Or I can do it as fractional, like 3 or 5 over 2. So either one works. You can use the decimal equivalent or the fraction. Plug it in. How much are they going to be worth? $62 shoes now, in 2.5 years from now, assuming you're increasing at the same rate, how much are they?
$70.
Oh, sorry, I got 2 people saying. What?
That's just a question.
Okay, that's your question.
The 2.5 over 2, could you solve it like what we're going to do with like take the square root and
Yeah, you could. Yeah. You could take the square root and take that to the 5th power. But it wouldn't help me. Obviously, this wouldn't be a no calculator problem. I'd have to use a calculator system. So it wouldn't help me in doing that. But yeah, you can. What was your question, Parker?
I was just saying what it was.
Oh, how much is it? How much
I
are
got
you?
$70.04.
$70.04.
Yeah.
All right, so 2.5 years. 5% increase. That's probably pretty reasonable. There we go. That's how much they are in 5 years. Yesterday we mentioned that you can go back in time. Once you have a model, which in this case is our exponential function, you can use that, assuming again that there was a 5% increase going backwards in time, sort of thinking about historical prices of shoes. But how would you deal with it if it was first 9 months, and then you're going backwards? So what do we do different? First of all, how many years is this?
3/4.
Yeah, that's 3/4 of a year. So obviously I'm going to have to make that 0.75 or just use the 3/4. But then, what does the ago part tell me? Yeah, negative. Gotta go backwards, not going forward. So I gotta make sure I'm using this negative part. So I have the same equation, but now it's A of negative 0.75 is equal to 62. 1.05. Good luck to the negative 0.75 power. How much were the shoes 9 months ago? $59.77. Not a huge change, but it is a difference. So you can see that exponential functions, they're a great modeling tool. But again, you're going to have to make some assumptions. And one of those assumptions would be my rate doesn't change. Any questions on A through C? What we're doing there? This stuff's not that bad, is it? All right, how about this one? Right, using no radical sign and using only positive exponents. So we got 4 of them here. You guys want to try these first, and then why don't we do that? Why don't we try them first, and then we'll check in on the answer.
You're giving us false hope while you're trying to yellow.
No, that's not yellow.
That's totally yellow.
No, this sorry. Sorry.
Well, 1/3 is like melons.
Here we go. So we're going to change this out of a radical into an exponential. So it looks like this: 27 a to the negative first b squared. Because it is the sixth root, it's the same thing as a 1/6 power. And now I have power powers. Everything on that inside is going to get raised to the 1/6 power. 27 is going to get raised. This negative first power is going to get raised, and this 2 power is going to get raised. We get 27 to the 1/6, a to the negative 1/2, which means it's going to have to move down, and then b to the 1/3. So here's the deal. In these problems, when you have underneath a radical, or as a base, you have numbers that are perfect root numbers, perfect power numbers. That's a perfect cube, right? 27 is 3 to the 3rd. When you have those, you must rewrite them as an exponential number so that you can simplify further. It's not, you look at that and you go, wait, 27, there's no factor of 27 that's a perfect 6. You're right. But if I change 27 to 3 to the 3rd, and then raise it to the 1/6, now it becomes 3 to the 1/2, or the same thing as the square root. Yes? Oh yeah, that shouldn't be 1. Yep, you're right. This should be negative 1/6, not 1/2. All right, there we go. You good now? All right, go back to the 3 to the 3rd thing. So that simplifies to the square root of 3, or 3 to the 1/2 power. So once I have 3 to the 1/2, a to the negative 1/6 moves down and becomes a to the positive 1/6, and b to the 1/3 just stays up where it was. And that's as far as it goes. Anyone have that? A couple of you guys. On B, we're going to change all those to exponentials. So tell me what it looks like as an exponential.
X to the 1/3.
X to the 1/3
Times X to the 1/6.
times x to the 1/6
Over X to the 1.
over x to the 1. Okay, very good. So now we have a situation where we had like the previous problem. We've got a situation that allows me to break this one fraction into, oh, well, I don't have to do this because I'm multiplying. Never mind. I was thinking addition and subtraction. We can simplify the numerator. Like bases add their powers. So x 1/3 plus 1/6. X to the 1/5. All right, got a little work to do there. So common denominator, got to make that happen on the top. So 6. It's the same thing as saying x to the 2/6 plus 1/6, which is x to the 1/2 over x to the 1/5. And then that is a quotient, which means I can go ahead and subtract. Again, thinking about common denominators, 1/2 minus 1/5. Same thing as x to the 5/10 minus 2/10. X to the 3/10. And there you are. Questions on A or B? Just kind of go step by step. Don't try and skip. Okay, let's try these next two. Again, we'll take a little pause, give you a chance to work them out, and we'll see how it went. B is I've got this 3x to the negative 1/3 is multiplying by this binomial. So look at this. 3 adding those exponents together, and this just becomes 3. When I do 3x to the negative 1/3 times the negative 4x to the 4/3, the 3 and the negative 4 are not being affected by the powers at all, so they just multiply together and get to negative 12. Now I take my bases and I add the powers of negative 1 plus 4 is 3/3, which is just x. Meaning my answer is 3 minus 12x. And then what? Don't do D? What? Oh, you didn't do D. All right, not a lot in terms of simplifying can be done on the top. But again, I recognize this as one fraction that can be split into 2. I have 9a to the 1/2 b to the negative 1/2 divided by 12ab to the negative 3/2. And then subtracting from that is this 6a squared b to the 1/2, all over the same thing. And now, since they're separate like this, now I can start to do my properties. I got a bunch of quotient stuff going on here. So 9/12, both of them divisible by 3. So I get a 3, and I have a 4 on the bottom so far. A to the 1/2 over A. Now, this A on the bottom is actually the same thing as A to the 2/2, but it's A to the 1st. So I've got a negative thing going on. If I were to bring the A to the 2/2 to the top, I'd have 1/2 minus 2/2, which makes A to the negative 1/2. So what I like to do is if my if I see that I'm going to end up with a positive in the denominator by moving the top variable down, I will go ahead and do that. So I'll just move the A to the 1/2 down. It still becomes subtraction because I'm switching the positive 1/2 to a negative 1/2 power when it moves to the denominator. And that means I have an A to the 1/2 down here. The B's, I'm going to end up with a bigger power, positive power, when everything moves to the top. So negative 1/2 plus 3/2 is 2/2, which is just B to the 1st. Do the same thing on the other one. 6/12. Obviously, I'm going to have a 2 on the bottom, A on the top, and B to the 2nd on the top. That's as far as we can do it. Oh yeah, where's the 2? Give me 2, not a 6. There we go. All right, how are we doing those? A through D. Last one. A little review for some test stuff. Do a little test review right now. All right, so for the first one, the car. Think about always setting up your generic formula and then plugging stuff in based on what you have. So we're looking for how much is it worth in 3 years. We're looking for the A of T. We want that to be 3 years, 4 months, which is 3.33 years. And I started with a $14,000 beginner car. What is that? And it was depreciating. So actually, we're not going to add. Depreciating means we remove 14%. And we're going to do that every year for 3.33 years. So a depreciation will be a value less than 1. An appreciation will be a value bigger than 1. So we plug all this in. 0.86 to the 3.33. Tell me the number again. $8,649.63. So that's how much your car will be worth. Less than 3.5 years. Wow, that's depressing. I go to the home. So this one we're looking for a rate. take a radical here, a root of something. So 1 plus the r to the t. Now, we purchased it for 260, so that's my original number. 6 years later, it's worth 287. That's my AT amount. It's supposed to be a 7. That's 7. That's supposed to be a 0. And then we are figuring out what is this rate. It's appreciating, so I'm going to have to add r. If it was depreciating, if the value was smaller 6 years or 6 years ago, then I'm going to have a negative r in that thing. And we're doing this for 6 years. So we divide 287 by 260. Somebody tell me what they get. 287 by 260. 1.103 is equal to 1 plus r to the 6th power. So how do I undo a 6th power? I take a 6th root. I have to take a 6th root of this thing. And when I take the 6th root of 1.103, you get, somebody help me. What'd you get?
1.0.
That's right. So you take the 6th root of 1.103, you're going to get 1.016. Now equal to 1 plus r. Subtract that 1, and we get a rate of 1.6%. So that's how much it's increased every year since we purchased the home for the last 6 years. Ta-da!